All right, Chemistry 3101. We left off with this problem here, and we were looking at some E2 reactions and regioselectivity. So remember, selectivity. Imagine you're being, you're at a buffet and you're being selective, right? It doesn't mean that you're not going to pick one thing, right? Let's say there's rice and then there's potatoes. You're going to be selective for one over the other, right? You're going to select, you're going to have more rice and less potatoes, right? So selective. So you're selective for one over the other. Just means you're still going to get both. So if we look at this compound here, this is our alpha carbon right here. We have two types of beta carbons. We have this beta carbon here in blue, and then we have this beta carbon here in black. And so we have two types of beta protons, don't we? We have the beta proton in blue, and then we have the beta proton in black. And so if I have ethoxide, right, if I have ethoxide as my base, is this going to pull off preferentially the blue proton or the black proton? Could anybody tell me that? Exactly. It's going to pull the black one off preferentially because it's an unhindered base. So let's scribble that down here. This is an unhindered base. And so it's preferentially going to make the Zaitsev product. So we can draw our mechanism like this. It doesn't ask us to do this, but I'm going to do it anyway. So we're going to pull off this proton, make the pi bond, and lose the chlorine. And so our, oops, where's my black pen? Our Zaitsev product is going to look like this, where we have, no, where we have a double bond here, like this. Okay, and then we have these CHEM dimethyls. So this is Zaitsev, and this is going to be our major product. Major. Okay, the minor product is going to result from pulling off the blue proton, and that would give us this compound. So this is going to be our Hoffman, and this is going to be the minor product, like that. Okay, let's take a look at the next two problems together. It's not something I normally do, but we have an alpha carbon here because it's the same substrate both times. We have the blue type of beta proton, and then we have these black protons here. So first we're going to start with hydroxide. Is hydroxide a hindered base or an unhindered base? Hydroxide, just OH. It's an unhindered base, right? So unhindered base. So it's going to pull off the black proton preferentially. So we could draw the mechanism for that. It's going to pull off the black proton, which is going to give us the Zaitsev product like this. And so our major product, when we pull off the black proton, is going to be this guy like this. So this is our major product. You can write Zaitsev in there. And then our minor product is going to result from the removal of the blue proton. Oops. Blue proton like this. So this is going to be our minor product. But then if we switch the base to T-butoxide, that is a hindered base, right? So that's a big old hindered base like this. And so that's going to pull the blue proton off preferentially like this. And so the major product in this case, so now I'm just going to copy and paste these. So I'll just copy, paste these guys in here. But now major and minor have reversed. Okay, this is going to be the major product, and then this is going to be the minor product. All right, any questions about that problem? Zaitsev versus Hoffman. Hindered base gives us the Hoffman as the major product, and unhindered base gives us the Zaitsev as the major product. All right. So a little more about these alkenes that we're making. Sometimes we can get cis and trans alkenes. So let's say we were doing the dehydrohalogenation of 3-bromopentane. There's symmetry in the molecule. Here's our alpha carbon. This is beta. So we have one type of beta proton, right? These two protons in red, there's no difference between the two. And so when your base, in this case your ethoxide, pulls off one of those beta protons, like this, to make the double bond, we could actually end up with the trans product, or we could end up with the cis product. And in this case, it says here, that we're going to get the trans as being the major product. Why? Because it's not only the kinetic product, right? Because it's got the lower activation energy. So trans is kinetic product, but it's the more thermodynamically stable. So we'll put here EA. So we'll say trans is kinetic, and thermodynamic product, right? In this case that's shown here. Says, yeah, use this energy diagram in the Hammond postulate to postulate why the trans isomer is formed stereoselectively. Well, I've already gone over this with you. It says that the transition state is going to more closely resemble the product than the starting material, and the product is lower in energy. So anyhow, not much more than that. I think it's not the greatest question in the world. So let's move on to stereospecificity. So before we get into this, let's think about the word specific. Before we said selectivity, it means choose more of one than another. So you're still going to choose both. But when we're talking about specificity, so I'm kind of running out of space here. So I'm just going to hear specificity. Let's use a pen that's going to work. Specificity. It means choose only one. Okay, so when a reaction is stereospecific, we're not going to end up with a mixture of cis and trans. We're going to end up with one or the other, the E or the Z compound. So check this out. How do you know when a reaction is going to be stereospecific over stereoselective? I can tell you very quickly. In stereoselective, it's when you have 2 or 3 beta protons to choose from, okay, on your beta carbon. When it's stereospecific, you have only 1 beta proton. You only have 1 measly beta proton. So look at this molecule very carefully. Okay, hopefully everybody can identify the alpha carbon. It's the one with the halogen attached to it. We look at this beta carbon here. There's no hydrogens attached to that beta carbon. It is attached to carbon, carbon, carbon. So it has no hydrogens attached to it. But if we look at the other beta carbon, this one here, it has 1 beta proton attached. This guy here. So this is the only beta proton available. Therefore, this is going to be stereospecific. Okay, so now you have to decide, once this does the elimination, do you get the E product or do you get the Z product? So if we treat this molecule with sodium methoxide, okay, what they're saying here is when you do your E2 reaction, so you remove the proton, form the double bond, well, it's not the prettiest arrow, form the double bond, lose the leaving group, you only end up with this compound here. Okay, this is the only one you get none of this. Okay, now why do you get none of that compound? Well, we're going to get into that in a second. First, can anybody tell me, is this the E compound or the Z compound? Did anybody identify this as an E alkene or a Z alkene? This would be a Z alkene, right? We have this group as being higher priority, and this group is being higher priority. So therefore, this is the Z product, the Zusammen product, okay? So we don't get any of the E alkene in this case. None of it. What does it say here? Now why is this E? This is labeled incorrectly. Sure, E and Z. This is wrong, okay? This is in the notes here. This should say only the Z isomer is formed in this case. All right, that's a mistake. Okay, but anyhow, let's get back to it here. Okay, stereospecificity. So how do we figure out whether we get the E or the Z product? Do you want me to give you the Sparks Notes version of it very quickly? Okay, I'll tell you the very fast way of doing it. Okay, it's this. Let me zoom in on this compound. Can everybody hear me? Give me a thumbs up. Okay, cool. I just want to make sure. Okay, so let me give you the Sparks Notes version of it. Here it is. Let me just So we're just going to look at this compound and we're going to study it, and I'm going to give you the explanation as to how you solve this problem very quickly. Now, why is that not making a box? Come on, iPad, do your thing. There we go. All right, here's the answer. So what you do is the alpha carbon and the beta carbon. So the alpha carbon has the halogen on it. The beta carbon has one proton. All you have to do is draw the dash and wedge structure like this so that the hydrogen and the bromine are on the plane of the page. That's it. And they have to be on opposite sides of the bond between the alpha and the beta carbon, okay? That's all you have to do is you have to have the bromine and the hydrogen drawn in the same plane, and they have to be in the most stable conformation as is shown here. And then all you have to do is draw the mechanism and you're done. So if you're like, I'm not understanding what you're saying, well, trust me, I'm your teacher. I'm going to go into the whole details of it. But that was the short version of it, okay? So to rationalize the stereospecificity, now I'm going to give you the longer explanation. You have to look at the transition state. What you have to do is you have to put the carbon-hydrogen bond, that's this bond, and the carbon-bromine bond, that's this bond. You have to put them into the same plane as the pi bond that's going to be forming. Where are you forming the pi bond? You're forming the pi bond right here. So they have to be in the same plane. So we say that the beta hydrogen and the leaving group are coplanar to each other. Okay, so not only do they have to be coplanar, they also have to be what we call anti-periplanar. Okay, so there's two conformations, or two rotamers is what they're calling it here, where the beta hydrogen and the leaving group are coplanar. There's this one where they're staggered with each other, so you can see they're coplanar here, or there's this one where they're eclipsed. So it's not going to pass through an eclipsed transition state because it's too high energy, and so you have to put the two groups, the hydrogen and the halogen, in the same plane, but they have to be anti to each other, right? You guys remember anti? Okay, so the groups must be anti to each other. After that, you just eliminate the hydrogen and the bromine, and you can see that in this case, the methyl group and the tert-butyl are going to be on the same side of the double bond, and the phenyl and the hydrogen are going to be on the same side of the double bond. All right, and that's all you have to do, is nothing more than that. So again, when you look, you see that the methyl and the tert-butyl, when you do the elimination, they end up on the same side of the double bond, and the phenyl and the hydrogen, they end up on the same side of the double bond, and there you go. So you end up with your E compound in this case, and that is all you have to do, my friends. So a little more about this whole stereospecific elimination reaction. Now, you heard this word come out of my mouth just a few minutes ago. I said anti-periplanar, and the word that I taught you before, I think, was coplanar, anti-coplanar. And all that it is saying here is that this angle, okay, this angle here is not always exactly 180 degrees, okay? Sometimes it's close to 180 degrees. So we don't say that they're coplanar. We say they're periplanar because it's close, okay? It just means they're close to being coplanar. And so again, the hydrogen and the bromine, the word that's correct is they have to be anti-periplanar. They have to be in the same plane, but they have to be anti to each other. It doesn't have to be exactly 180 degrees, but it should be close to 180 degrees. All right, that's all it's saying. So with all that in mind, and if you're sitting at home and going, man, this is tricky, I'm not really sure about this, okay? Number one, you're right, okay? You're totally correct in thinking that. It's not a simple concept. And number two, I've seen many students master this subject. How? By practicing it over and over and over. So we're going to go over these two examples. And obviously in one we're going to get a cis, one we're going to get a trans, okay? But it's just kind of getting us used to doing it. Okay, so it says, assuming they proceed through an anti-periplanar transition state, predict the products of these reactions. So let's look here. You can see that our bromine, our leaving group, and our hydrogen that we're going to be removing, they are coplanar, right? They're anti-coplanar. If you were to draw the Newman projection of this, okay, so this is how I would do it. I look down this bond, okay? I'm looking from here to here, and what do I see? Do I see? Okay, so I have my carbon in the back, I have my carbon in the front. On my carbon in the front, I have my hydrogen going down. I'm going to have R2 going off here. I have R1 up and to the right, like that. In the back, I've got my bromine going straight up, so it's antiperiplanar to the hydrogen. Then I have another R2 group that's going to be going down to the left, like this, and I have another R1 group that's going to be going down into the right, like that. So now the mechanism is going to be like this, where the base is going to abstract the proton, you form the pi bond, and you lose the bromine. So what's going to happen is you're going to end up forming your double bond. I'm going to draw it like this. Okay, there's my double bond. Okay, I'm going to make this carbon, this red dot, I'm going to make that this carbon here, and I'm going to make this green circle in the back. Okay, I'll make that this carbon here. I know the green isn't the best color on the screen, but we'll do it like this anyhow. So you can see that on the red carbon, the one in the front, you have an R2 group going down like this, and then you have an R1 group coming down like this. On the green carbon, the one in the back, you can see that you've got your R2 group going like this, and your R1 group coming like that. Give me a thumbs up if you see that after the elimination. Give me a thumbs up if you follow me on this. Even if you're like 60, 70% of the way, because you will have to try it. All right, so let's do the same thing with this one. The next one, you can see the bromine and the hydrogen are antiperiplanar to each other. We're going to look down this carbon-carbon bond with our eyeball. So we'll draw the human eyeball here, my wonderful sketches. Okay, so now we've got the carbon in the back. Okay, and we've got the carbon in the front. On the carbon in the front, I've got my hydrogen going down. I've got R2 going up and to the left. I've got R1 going up into the right. I've got my bromine that's antiperiplanar, so that's good. And now I've swapped the groups in the back. I've got my R1 going down into the left, and I've got my R2 group going down into the right. So if I do the same strategy, if I highlight the carbon in front in red and the carbon in back in green, okay, I'll draw my double bond like this. I'll draw the red carbon in front, the green carbon in the back. If I look at the red carbon, it's going to have an R2 group over here. It's going to have an R1 group over here. The carbon in the back is going to have its R1 group off and to the left. And its R2 group is going to be going back into the right like that. Give me a thumbs up if you follow me on that. All right. I know my students are usually very good at Newman projections, but that is how you do a stereospecific reaction, okay? And again, I always ask a question about this on the quiz. There's usually a question about this on the exam. So in the first case, we ended up with these two groups and these two groups being the same. So this would technically be a cis compound and this would be a trans. But sometimes we just have to use E and Z. So again, if you have two beta hydrogens, it's not going to be stereospecific. It's going to be stereoselective for one over the other, right? Because you have two different rotamers where there's two beta hydrogens that could be antiperiplanar to the leaving group. And so again, in this case, when you have two beta protons or more, okay, it's going to be stereoselective. Okay, so you're going to end up with a mixture of cis and trans, or E and Z, and you have to choose, well, usually it's going to be based on steric hindrance, which one is going to be the major and which one is going to be the minor. So I feel like I've harped on this enough to you already today. Like I've really given you the business with stereospecific versus stereoselective. So again, you go to a buffet. If you're selective for something, right, it means you're going to pick more rice and less potatoes. But if you're specific, you're like, I'm only getting ice cream. I'm not getting anything else. It's the only thing I'm eating. I came here and I paid my $30, but the only thing I'm eating at this buffet is ice cream. Forget the rest of it. You're very specific. Okay? Give me a thumbs up, or are there any questions? Please, if you have a question, go ahead and ask me now about stereospecific versus stereoselective. And even if you don't want to ask me now, what could you do? Feel free to fire me an email after class, or if you want to meet with me on Microsoft Teams, I'd be happy to re-explain this topic to you. Why? Because I remember the first time I learned it back in 1995 and struggling with it a little bit. And it took me, you know, probably a little bit of time in the library of practicing it before I said, okay, yes, this is stereospecific, this is stereoselective. So my job as your instructor is to try to explain this stuff the simplest possible way. So let's see if I can get you to pick the right answer here. If this is my alpha carbon on this alkyl halide, well, it's alkyl and aryl, right? But anyhow, we've got a beta proton, or sorry, a beta carbon here that's got no hydrogens attached to it. But on this beta carbon, I've got two hydrogens, don't I? I've got a hydrogen here, oops, like this, and then I also have a hydrogen like this. So I've got two beta protons. Will this elimination, if I treat this with a strong base, let's say I'm treating this with sodium ethoxide, is this reaction going to be stereospecific or stereoselective? Could anybody answer this? If I have two beta protons, exactly. Woo! All right, that makes me very happy. Okay, thanks, Kiana. Thanks, Katana. So this reaction is going to be stereoselective. Okay, so if it's stereoselective, you don't have to do any of that Newman projection stuff. Forget it. You don't have to do it. All you're going to do is draw the E and the Z, and then you're going to see whichever one is less sterically hindered. That should be the major product. If you want to draw a mechanism, knock yourself out. If you don't, that's fine too. But I'm going to do it here. So let's just practice our E2 mechanism. Okay. So what we're going to end up with is this. So we've got our aromatic ring. And then we have our double bond that's going to be formed here. And then we have our tert-butyl group. Our tert-butyl group. So this is the trans compound. And then we're also going to get the cis. So I don't know. It doesn't even matter which proton gives you which one. It doesn't matter. Just draw them both. So there's the trans. And now we're going to draw the cis like this. So if I draw the trans and the cis, which one of these do you think is going to be the major product? Which one of these looks less sterically hindered to you? And it's not a trick. I would never try to fool you. Exactly. Thanks, Katana. Thanks, Kiana. This is the major product. Exactly. Major product, minor product. Just like that. All right, so let's try the next one. Sarah, to answer your question, yes. If there's two beta hydrogens, it's going to be stereoselective. And if there's just one, it's going to be stereospecific. So Sarah, my question is to you, on this one here, is this going to be stereospecific or stereoselective? The example that's shown at the bottom here. Exactly, because there's only one beta proton. Hot dog. So, and is it in the right conformation for us to draw a Newman projection? Absolutely not, right? Because you can see the hydrogen is going back into the page and the bromine's going back into the page. So they're not coplanar with each other. So we need to rotate the bonds so that they are coplanar to each other. So let me show you how I do it. I'll show you the Mr. Dion way of doing it, and then you can see what you want to do. So let's just see here. Yeah. All right. So here's what we're going to do is we're going to draw the Newman projection. Let's draw what we see when we look down this carbon-carbon bond. Okay, so I'm going to do my best here. So we have our carbon in the front, we have our carbon in the back, right? And our carbon in the front, we've got our phenyl group going straight up. We have our hydrogen down here, and we have our methyl group coming down here. I'll just label it as CH3. In the back, we're going to have our tert-butyl group going straight down like this. Then going up into the left, we've got the bromine like this, and then we have our hydrogen up here. So what we need to do is we need to get the bromine and this hydrogen to be anti-periplanar to each other. So what are our choices? I mean, what I'm going to do is I'm going to rotate the bond, and I'm going to put the hydrogen over here. I'm going to put the methyl group up here, and I'm going to put the phenyl group down here when I rotate it. okay? So I'm going to rotate it 120 degrees. So I'm going to rotate this 120 degrees, and I'm going to redraw. There's my carbon in back. There's my carbon in front. So I didn't change anything in the back, so I'll put my bromine here, put my hydrogen here, and put my big old tert-butyl down there like that. So now I've rotated it, so the hydrogen is going to be here. The methyl group is going to be up here, and the phenyl group is going to be way down there. So now I don't have them vertical, but at least they're anti-coplanar, right? You can see that the hydrogen and the bromine are coplanar. Everybody with me on that? Give me a thumbs up if you're with me on that so far. Okay, awesome. So what I'm going to do is I'm going to highlight this carbon in red, the one in the front. I'll highlight the one in the back in green, like this. Let's draw our carbon-carbon double bond, like this. This will be our carbon in the front. This will be our carbon in the back. And so we see that on the carbon in the front, we've got a phenyl group and a methyl group. So I'm going to draw the phenyl going down like this. I'm going to draw the methyl going down like that. Now you can see the methyl and the proton are on the same side of the molecule. So I'm going to have my proton over here like that. And what else? Yeah, and then I'm going to have my big old tert-butyl. There's my yellow highlighter. I'll put it like this. So there's the phenyl and the tert-butyl. They're on the same side. So I'll draw my tert-butyl like that. And there's the final product. Boom. Give me a thumbs up if you follow me on that. Or stop me if you have a question. Okay, and when was the last time you saw me write this on a slide? Practice. Okay, you're going to have to practice it quite a bit. The bromine was eliminated, right? That's the whole purpose of the reaction, right? The whole purpose of this reaction is you're treating it with sodium ethoxide, right? And the ethoxide is going to grab this proton, make the pi bond, and lose the bromine. Does that help, Katana? Cool. All right. There you go. It's just you can't draw the mechanism on the Newman projection because you can't show the pi bond being formed, right? If you were to try to draw, right, it's taking the proton. There's no way to draw the pi bond being formed. You can't really do that, but you could show those two arrows if you wanted to, and then we form the pi bond. So there you go, stereospecific versus stereoselective. It's always something that I look forward to teaching my students because it's kind of challenging, and it's really fun to watch students master this and get really good at it. You can imagine, I always have some students in class who are interested in things like MCAT, DAT, you know, ACS, of course, right? And those kind of exams, they love these kind of questions, right? Because it asks you so many things at once, you know, so they kind of kill a whole bunch of birds with one stone. So let's turn over to the next slide and just a little bit more about stereospecificity. It says, consider the dehydrohalogenation of a cyclohexane derivative where the leaving group is attached to the ring. I mean, given the whole anti-periplanar requirement, an E2 elimination can only occur when you have a leaving group in an axial position. So this is kind of the take-home message here. You can only have an E2 on a ring if the leaving group is in an axial position. If it's in an equatorial position, it doesn't happen. Okay, it's got to be axial. And if you're like, well, why is that? Because it's the only way that you could have a leaving group being anti-coplanar to it. It's got, if you have the leaving group pointing up in axial, that means that the beta proton would have to be down and axial. Okay, so you could remove that beta proton or this one, either way. But in here, there's nothing that's going to be anti-periplanar to it. Here they show the Newman projection of it. I would never get you to draw the Newman projection of a ring like that. So if it helps you to look at it, be my guest, but you don't have to. So that brings us to this question here. It's a great question. You can see how this would be a great quiz question or something. It says, which of these two molecules will not be able to undergo an E2 and why? It might be helpful to draw the chairs. You don't have to draw the chairs though, okay? Let's put here. We'll put here, not required to answer the problem. You don't have to draw the chairs. Let's think about this very carefully. So if this chlorine is pointing up in axial, that means that it could be anti-periplanar to a beta proton that is pointing down an axial. So if I circle this proton in red, what is the orientation of this proton? It's going down, but is it axially or equatorial? Can anybody answer that? Is this proton axial or equatorial? It's axial, exactly. Right? Because if you have up an axial, that means the next hydrogen is going to be down and axial. So that means that this one here is also down and axial. And so we could get an elimination occurring on this molecule. But if this chlorine is up and axial, that would mean that this is up, up and equatorial, and that this proton here is up and equatorial. And so an E2 reaction will not work on this molecule. Give me a thumbs up if that makes some sense to you. You have to have the leaving group up an axial, and the beta proton would have to be down an axial. Exactly. There we go. So it says rationalize the products formed in these reactions. So if we look at this reaction here, okay, if this chlorine, if we imagine this chlorine as being down and axial, that would mean that this group here is up and axial. So that would mean that the proton that's here would be down and equatorial. So you cannot eliminate that proton. However, if you look here, if we draw this proton in blue, this proton would be going up and axial. And so you can do an elimination with this proton. And so that is why this is the only product we get, is the one where the double bond is formed between this hydrogen and this chlorine. Now, in the second example, if the chlorine is going up and axial, that would mean that this hydrogen here is going down and axial. And if we pulled off that proton, we would form the double bond that would result in this product in the red box. If we pulled off this proton, this one here that's going down and axial, that would form a double bond here, and we'd end up with this product. So that would form the double bond here, like that. Now, the whole thing about fast versus slow here, let's see here, E2 reaction is fast and E2 reaction is slow. The reason why this one is going to be slow is because if you have this leaving group in an axial position, then the tert-butyl group is going to be in an equatorial, is going to be in an axial position, and this is going to result in 1,3 diaxial interactions, whereas here the tert-butyl group is going to be up and equatorial, and so you're not going to have 1,3 diaxial interactions, and so that's why the first one is going to react slower than the second one. It's because the tert-butyl group would be in the axial position. So there you go, a lot to unpack in that example, but a very pertinent example nonetheless. So when you're drawing the products of E2 reactions, you might get a little, overwhelmed at times because there's so many products that can be formed. It says consider, everything that can happen. So is the reaction going to be stereoselective, okay, or stereospecific? So stereospecific is when we have one beta hydrogen, and stereoselective is when we have two or more beta hydrogens. And if you can get different regioisomers, what's going to be the major product? What's going to be the minor product? Is it going to be the Hoffman or the Zaitsev? And that you have to take the base into account. And the only way to master this material, and this is out of the words of David Klein, the only way to master this material is lots of practice problems. It's really the only way that you can do it, is a lot of practice. If you practice just the night before a quiz, it won't work, right? You got to do a lot of practice. And so what I thought we would do is take a look at these two problems here. So yeah, so why don't we take a short break, and then that will give you a chance to try these. and then we'll come back and we'll take a look at both of them.